So we've been looking at examples of initial value problems and how we solve them numerically, and I want to do two more examples of higher order equations. So again, the second order equation here as we've had in the past, but now a more complicated equation. This is from section 7.2.1. It was a force spring mass system that we looked at. So it's a second order equation. You notice I've written in a little bit different form than in that section because I put it in the form that we use here. So we have the highest order derivative is equal to f, which is everything else. So it's everything is a function of t, anything is a function of u, and even including the first derivative now. So let's rewrite this as a system of two first order equations. It's second order, so capital N is 2, so we'll write it as a system of two first order equations. We'll include the initial conditions. I'll come back to that. So the way we do this, as we've done in the last couple of examples, is we introduce two new variables, u1 and u2. u1 is equal to the original dependent variable u. u2 is equal to its derivative, so u dot or du dt. And then we take the derivative of both of those. So u1 is u, so u1 dot is u dot, but from our definitions, u dot is u2. u2 is equal to u dot, so u2 dot is equal to u double dot. And u double dot, once again, whenever you get to the highest, the last equation, the highest order derivative, you get that from the original differential equation. So it's the right-hand side of that original differential equation. That's the f. So in this case, that's minus g minus f over m cosine omega t plus minus k over mu minus c over mu dot. And you'll notice I've highlighted here the u and the u dot because once again, you're not done yet. You need to convert the old variables u to the new variables u1 and u2. So u is u1 and u dot is u2 from our substitution. Now, as far as the initial conditions, it's second order, so we need two initial conditions. So we specify the position at t is equal to 0, and we specify the velocity at t is equal to 0. So u0 is the position, v0 is the velocity at the initial time t is equal to 0. So in terms of the new variable, u is u1, so that means u1 at t is equal to 0 is u0, and u dot is u2, so u2 at t is equal to 0 is v0. So now, again, you get rid of these in the middle here, and so this is our system of equations, two equations for two unknowns, along with our two initial conditions. And so we could solve that using first order explicit method, first order implicit, Crank-Nicolson method, and here's what the solution would look like. So this is for an acceleration due to gravity of 9.81, mass of 1, spring constant 1, the c is the damping, this is the amplitude of the forcing, the frequency of the forcing, the initial position, and initial velocity. So if you put all those in, solve it numerically, then this is what you get. This, obviously, it's an oscillatory behavior. You can see it falls down because of the mass, and it wobbles back up and down for some period of time. This is for a long period of time of 100. The second example that we've seen, this is from section 352, was the two mass, three spring system that we looked at before. So we have a mass on the left, double the mass on the right. Their positions are x1 and x2, and then we have three springs, linear springs, connecting the two masses together and to the two boundaries to the left and the right. In this case, the wibbling and wobbling is just in the horizontal direction. So at that time, we looked at free body diagrams for these. So mx1 double dot is equal to f, or 2. So these were free body diagrams, and we applied Newton's second law to them for this mass, and that led to these two governing equations. So I wanted to show this example because now we have two second order equations. We need to convert those to a system of first order equations. So as you might guess, we'll convert the first second order to two equations, the second order to two additional equations. So we'll actually have four total first order equations. So two second order equations, 2 times 2 is 4, So we end up with 4 first-order equations. So let's show you how to do that. So so again, we have 2 dependent variables, x1 and x2. They're coupled together because they both appear in both equations, and let's convert that to a system of equations. So our new variables will be u1, u2, u3, u4. u1 is x1, u2 is x2, and then u3 is the first derivative of x1, and u4 is the first derivative of x2. Once again, we differentiate each of these 4 substitutions to get our new system of equations. So the first one is u1 is x1, so u1 dot is x1 dot, but you look, x1 dot is u3, so that's u3. u2 is x2, so u2 dot is x2 dot, but x2 dot is u4, so u4. u3 is equal to x1 dot, that's this third equation. Differentiate that, so u3 dot is x1 double dot. x1 double dot, we have to go back to the original differential equation. So this is x1 double dot, so bring the m over to the right-hand side, and that is x1 double dot. So you see that right here. Now this capital K is little k over m, so I've combined them here. So that's that. Once again, we don't want x1s and x2s, those are the old dependent variables. We want only u1s and u2s and u3s and u4s. So x1, what is that? That's u1, so u1. x2, what is that? Well, that's u2, so u2. Same thing with the fourth equation. So u4 is x2 dot, differentiating, u4 dot is x2 double dot. x2 double dot is from this equation, divide through by the 2m on the right hand side, and that gives us this. Then x1 is u1, x2 is u2, so u1 and u2. Oops, I forgot the t here. There we go. All right, so these are gone. So we have 4 equations for our 4 unknowns, u1, u2, u3, u4. Again, I won't go through the details of the numerical solution. I'll just give you the results for a particular set of parameters. Here it is in matrix form, so it's a 4x4 system of first-order equations. You see the first-order derivative is on the left. Your 4x4 coefficient matrix times the 4x1 solution vector that we're looking for. So initial conditions, let's say that the original position of x1 is 0 and its velocity is 0. The original position, so that t is equal to 0, of x2, the right mass, is 1, and its initial velocity is also 0. So again, we have to translate these into the new variables. x1 is u1, x1 dot is u3, x2 is u2, and x2 dot is u4. So these are the new initial conditions in terms of u1, u2, u3, and u4. So here's a sample solution of that. So once you get the solution, again using first order implicit, explicit, or Crank-Nicholson for our system of equations, x1 and x2, which are equal to, so x1 is equal to u1 of t, and x2 is u2 of t. So you'll get as a solution u1, u2, u3, u4 of t, but then when you go back to the original variables, we just need x1 and x2, which are the u1 and u2. So u1 or x1 is the solid line, and you can see it satisfies the initial condition, 0 at t is equal to 0. And then the dashed line, that's x2 or u2, which starts at 1. And you'll notice it actually makes sense. So the dashed line is the right mass. Remember, the right mass is twice the mass of the left mass. So it's like 2 people standing next to each other holding hands, wibbly-wobbly back and forth, and one is twice the mass of the other. So the one that's twice the mass is just going back and forth, kind of oblivious, seemingly oblivious to the presence of the lighter mass, whereas the lighter mass is kind of getting whipsawed back and forth as it oscillates. because of the larger mass. All right, so those are two examples, two more examples of higher order equations that then lead to systems of equations that we can solve. And these are examples that we saw earlier in the semester. Okay, we'll look at a couple more comments, just two brief sections talking about additional methods for ODEs in the next video.